We can drive conservation of energy in a bunch of different ways, and we did it differently in thermo than we're going to do it here. But since we have Reynolds transport theorem, let's go ahead and use it. It's very handy for this, and you did this in your worksheet last time. So if you have Reynolds transport theorem, remember your B and your beta. B, if your system law is E dt, B is your E. Well, E for us is internal and kinetic and potential energy. Okay, where Z is the height, okay, the elevation. So beta is just take that and divide by M, right? We could call it little e, because that's what we did for specific values, which means little u plus v squared over 2 plus gz. So we're dividing by m. Okay, so plug that little e in for your betas into your system law, and the non-derivative side on the left-hand side, in this case, let's just throw it over to the right, and we're going to get d dt is our unsteady term, remember, over the whole control volume, rho e dv, d volume, plus the integral over your control surface, rho e v dot n dA equals q dot minus w dot. Okay, so the v dot n is always in these Reynolds transport theorems because it's the velocity that's going to carry that energy with it. Okay, it also carried the momentum with it and the mass with it. So those are always in there, the v dot n equations, part of it. So x here, again, is our unsteady part, the rate of change inside the CV. So if that's steady state, that term just goes away. Y is the total inlets and exits, basically. So that's the net leaving of energy leaving. And then this is the energy crossing the borders in form of heat and work. Okay. So remember from thermo, Q dot is positive for heat output, and W dot is positive for work output. So what we want to do, just like we did in thermo, is we're going to want to plug all these values in for E, the U's, the V's, the G's, and so forth. One of the things we also want to do is split our work, our W dot term, into the two types of work. One is work due to pressure. Okay, so the pressure of a fluid coming into a control volume kind of acts like a piston cylinder. Okay, and that provides work. But then we have another kind of work, and that's our shaft work, and that basically means our pumps and our turbines. Okay, so we want to split that out because a lot of times we're trying to figure out what's going on with those pumps or turbines, or we're given information about pumps and turbines. And our work from our pressure, that's going to give us pressure terms as well. We did this in thermo, and that's where our H's came from. Okay, so for our shaft work, again, that's just pumps or turbines, or it could be fans, something like that. In thermo, we also had compressors, but compressors tend to change the temperature, and that's kind of the difference between thermo and fluids. In fluids, usually we're not talking about big temperature changes. Thermo was all about big temperature changes and heat input and that kind of thing. So again, work is positive for work output, and for example, a turbine puts out work. It's negative for work input, and that would basically be our pumps or possibly fans in fluids. So let's look at the pressure part of the work first. Okay, the pressure work or the flow work. If you have this slug of incoming fluid here, let's think about the power of that. Okay, because power is just work over time. The power is force over velocity, or times velocity. FV or FU if you're talking about x direction. Our force was pressure times area. Let's plug in that V again. Rearranging this, you get P times VA. Remember what VA is? VA is Q. not our heat transfer Q. This is our flow rate Q. Remember, m dot is rho VA and Q equals just VA. That's, of course, if you're using V average. So that's a simplification. If you're not using V average, our pressure work has to be integrated basically over that whole inlet. But that's not going to happen. Okay. But let's just put that in there for completeness. Okay, so plugging this back into our conservation of energy along with our kinetic potential internal energies, we're going to get kind of a long equation. ddt integral over your whole control volume of rho times that little e, and that little e is u plus 1/2 v squared plus gz. Now I put a little cap on the u to distinguish it from our x component of velocity, because we have u's already in fluid mechanics. All right, so the cap means internal energy. Okay, so that's our unsteady term. We're not going to deal with unsteady normally, going to cancel that out. And then our inlets and exits, rho, and then our little energy, again, u plus 1/2 v squared plus gz, okay? And then we're also, when we plug this p times v times a business in, we can put in these terms, p over rho, v dot n dA, okay? So that basically comes from this right here, p times v dot n dA, okay? So in thermo, what we did was we took this u and this p over rho. Well, rho is actually 1 over little v, where little v is your specific volume. We're going back to thermo. So that's u plus p over rho. Okay, so this term here plus this term here is just h. Okay, and again, I put a little cap over h because we have HFs and HSs that we're using here in fluid. And that's all because little v equals 1 over rho here, specific volume. Okay, so if you rearrange that then, you're going to get your equation with h's. So the unsteady part, ddt, that doesn't change because we didn't have a PV in it, over your control volume, rho u plus 1/2 v squared plus gz, d volume, plus the integral over all your inlets and exits, rho times h plus 1/2 v squared plus gz times v dot n dA, dA equals q dot minus w dot s. Okay. So here, what I've done going through here is take the pressure work and plug that back in, bring it over from the left-hand side into the right-hand side. And I had forgotten my q dot minus w dot s here. So I just left the shaft work on that right-hand side and pulled the flow work back into here, and then that way we could get our h's. And this is essentially what we had for thermo. If we have steady flow, this whole term goes away. Fixed number of inlets and exits means we're going to break this up into summations. And as long as V is not changing, if we're using V average, we can simplify that as well and get that m dot in there. So what we end up with is q dot minus w dot s equals the sum over the outlets of our enthalpy plus 1/2 v squared plus gz minus our inlets, the same thing, enthalpy plus 1/2 v squared plus gz. Remember, that was our control volume equation from thermo. Okay, and again, the difference between thermo and fluids is now we're not going to have many differences in U because our temperature is not going to be changing a lot. Okay, if I look at a single inlet and exit, and that's normally what we're going to use in this class, is single inlet and exit problems, which helps us out because mass conservation is now m dot 1 equals m dot 2, and we can just call that m dot. And our energy conservation then breaks down to q dot minus w dot s. And we use this one a lot when we had pumps and turbines and that kind of thing. When we had heat exchangers, we had to use it with the sums. So m dot h2 plus 1/2 v2 squared plus gz2 minus m dot h1 plus 1/2 v1 squared plus gz1. Okay, thermo equation. Remember, be careful with this when you're using this equation. 1 has to be your inlet and 2 the exit. If you get those backwards, your signs will all be wrong. Okay, so that was the thermoform. Okay, we used our Reynolds transport theorem from fluids to come up with it, but what we ended up with was our thermoform. What we want to do is rearrange this a little bit to come up with our head form, which is our fluids form of it. So if we first of all just break this H, the little cap, or enthalpy, back into U plus PV, and then just totally rearrange this, what you're going to get is, so we have our P's in here, we're going to end up with a P1 over rho G plus a V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G. And again, this is steady state, average velocities, one inlet, one exit. So plus V2 squared over 2G plus Z2 plus W dot S over M dot G. So we're trying to get it in head form too. So we are taking the whole equation, dividing it by M dot G. Plus, we're out of room here, put the plus down here, plus U2 minus U1, so those are our internal energies, over G minus Q dot over M dot G. Taking the whole equation, divided by M dot G, took the H's, broke those back down into U's plus P over rho, and this is what we end up getting. So this term, W dot S over M dot G, that's our HS. We're going to call it head form of our work, shaft work. And this is what goes into our HF, or our frictional head losses. Okay, so basically we don't have a whole lot of heat transfer going on. The heat transfer that we have in fluids is usually from the frictional losses, so we kind of lump that together with the internal energy terms and just call it HF. We'll go through how to find HF when we get to chapter 6. For now it'll just be given, or else what you're trying to find. Okay, and again, this is the head form of the conservation of energy equation, because these are all going to have units of meters or feet. So be very careful with your units. Units can get very tricky with this equation. First term is the energy at the inlet. Second term here, meaning really those three terms. Mechanical energy at the exit. And then HS is your shaft head work. Again, that's W dot S over M dot G. And the head loss due to friction is our HF. Okay. Remember, if you end up with a negative HF, you can't have negative losses. You can't have negative, because that's a gain. And you're not going to get any gains from friction ever. Second law of thermo says you're never going to get a gain from friction. So HF always has to be positive, meaning if you get something negative, you know you've done something wrong. And these are the equations we are going to normally use. You'll probably get these memorized because we'll use them so much. Okay, so quick examples. The key on using this equation, the equation's not hard. It's easy to write it down, but the key thing that you want to be able to do is cancel out as many terms as possible. And you do that by carefully drawing your control volume. So, and it depends on what you're given and what you're trying to find, how you want to draw it. So this first one, you got an oil pipeline, repeating pump stations, and you want to find the pressure drop between pumping stations. Okay, so what you want to do for this one is draw your control volume with your inlet here and your exit here. Okay, I don't want to put my exit here because basically after each one of these pump stations, I could assume that it's at the same pressure. I'm not going to be able to find a delta P in my equation if I do that. Also, I don't know what's going on with that pump, so I don't really have an HS to plug in. So if I go between them, though, I'm going to be able to find what I want, and I'm not going to have to deal with those pumps. Okay, so here we're given Q. Again, watch your units. A barrel happens to be 42 gallons. You still got to go convert gallons to feet cubed. HF is 533 feet. What you want to do, find the pressure drop between the pumping stations, write your assumptions, incompressible, steady, single inlet and exit. So we have our simple equation. P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2 plus HF plus HS. That's supposed to be an F here. Okay, so we can cancel some things. Okay, so V is not 0, right? We got a flow going. V is not 0, but V1 and V2 are the same because the diameter never changed through there, and you have the same flow rate going through the whole thing. Since flow rate is V times A, right? Incompressible steady average velocity. Okay. If Q is V times A, then V1 is equal to V2. And therefore, we can cancel those. Okay. Z1, this is horizontal. We can assume it's horizontal. So Z1, if we draw our Z-axis here, coordinate system there, Z1 is also equal to Z2. So you want to draw your control volume so you have things that are equal or things that are 0, either way, and that's good. And the other thing we can drop out, between 1 and 2, we have no pumps. So you're always looking between your inlet and exit of your control volume. No pumps. Between. Don't look outside your control volume. That doesn't do you any good. So what you end up with is P1 minus P2 over rho G, just pulling that P2 over, equals HF. HF is a given, so we're trying to find P1 minus P2. That's going to be rho G HF, or specific gravity of our oil, gamma of the water, times HF. Comes out to be delta P equals 199 PSI. And you can do the math if you want. I'm not going to go through it. Okay, same situation, different thing that you're trying to find. Okay, instead this time let's find the pump size. So if we're trying to find the pump size, well, our control volume better include a pump. Okay, if I put my control volume here, so it starts at 1 and ends right here, the good thing about that is I know that the pressure should be the same at the same spot. I could alternatively put it right after this pump and then right after this pump, because I know right after the pumps they should be at the same pressure. Okay, so with that, you can go ahead and again just do the same thing. What we know is V1 equals V2, Z1 equals Z2. This time, P1 equals P2. Okay, so we're going to cancel a few different things out of the equation. And in fact, P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared. And you want to kind of do what I'm doing here. Write your whole equation, cancel terms, and really tell why you're canceling them. So plus Z2 plus HF plus HS. Okay. So again, P1 equals P2, so this time we can cancel that. V1 equals V2, so we can cancel our V's. Z1 equals Z2, not a whole lot left. HS equals minus HF. Okay, and we know that, that's minus 533 feet. Okay, so all we have left to do is a little bit of conversions with knowing that our HS is W dot S, or pump power, over M dot G. And so just rearranging, plugging in, I'm just going to give you the answer here. W dot S equals 1,690 horsepower Again, be very careful with units on this equation. You got a bunch of conversions to make. And horsepower is not, does not convert directly. You need to look up, there's like a 550, what is it, foot-pounds per second in a horsepower, I think. Okay, so stop here and do quiz questions 3 through 4.